Welcome to homework.
So for problem 15.200, we have this planetary gear system of the drawing, and we'll be given the angular velocity of gear C, which is 30 radians per second, and the angular velocity of gear D, which is 20 radians per second, both counterclockwise if viewed from the right, and we've been asked to calculate the angular acceleration of gears A and B, and the linear acceleration of the tooth of gear A at point 1. So for this problem, we will use some results that we derived from problem 15.199. That is that the angular velocity is 28.387 ahead plus 5.242 j hat radians per second, and that the angular velocity of the horizontal shaft is 25.49 17 I had again radians per second. As usual, in order to calculate angular acceleration, we better choose a rotating frame, and a convenient choice of a rotating frame will be a frame rotating with the horizontal shaft FH. Therefore, the angular velocity of the rotating frame would be exactly the one of the shaft. And using the typical formula expressing the angular acceleration in terms of quantities from the rotating frame indicated by the prime indices. So this is the angular velocity from the from the from the rotating frame, and this is the rate of change of that angular velocity from the rotating frame. Okay, we have we established that the angular velocity of the rotating frame is just the one of the shaft. An observer rotating with the shaft would only see the gears A or B rotating relative to the shaft. Let's write this as A relative to the shaft, angular velocity of A or B relative to the shaft, and that will be constant, as we indicated from the beginning. That will be constant, so there won't be any change, any rate of change for this relative angular velocity. Therefore, it is just this cross product, and it might be better. I hope this is clear. We can express this quantity as a vector difference between omega, the angular, yeah, the angular velocity of the system minus the angular velocity of the shaft. Which, basically gives us omega shaft cross product omega. Yeah, and if someone does the calculations anyway, this will give 133.626 k hat. This is in radians per second per second. And I have to mention again that this result diverges a little bit from the suggested answers at the end of the book, but I would like to insist on this specific result. This is the answer for task A. Let's go now to task B. We need the linear acceleration of point A of gear, no, excuse me, of point 1 of gear A. So from the typical formula, cross product of the angular acceleration times the vector position of point 1 plus the angular velocity, cross product is another product, which actually is equal to the linear velocity of point 1. And from the drawing, we know that the vector position of point 1 is minus 80 I hat plus 260 j hat millimeters. And V1, as we calculated back in problem 15.199, is typically omega cross product R1, and this gives us 7,800 k hat millimeters per second. So really quickly, if we do the calculations for each of the two terms, angular acceleration, cross product R1, this has only a z component, cross product position, we get this result. In millimeters per second, and the other term, cross product of the angular velocity times the vector of position, hat. This gives us 40,887.1 I hat minus, this one. And if we add the two, we get the final result in meters per second, 6.144 I hat minus 232.11 j hat meters per second. This is the final result for task B, and again it diverges a bit with the suggested solutions, but I would like to insist on that one.